during welding operation in heat affected zone, first of all one thing you should keep it in mind. In case of welding there is liquid fusion zone, there is heat affected zone and there is cold base material zone. These three zones are there, correct. Now, always you should keep it in mind, the absorption capacity of hydrogen is more in case of liquid than heat affected zone, which is solidified one, than cold metal zone. That means, you can write, I am writing L, heat affected zone I am writing H and cold material I am writing let us C. So, always you should keep it in mind, hydrogen absorption capacity is more in case of liquid, then heat affected zone, then what it is called cold base material zone. So, what happens during welding operation, once the weld zone start cooling, then this hydrogen try to escape from the liquid metal zone. So, it try to escape either in atmosphere as well as is try to move towards the direction of heat affected zone. Similarly, during cooling times this hydrogen also try to escape from cold material to you can say atmosphere. Okay. So, during that time generally what happens, this hydrogen entrapped in between this fusion zone and cold material zone, that is in heat affected zone the hydrogen is entrapped. This hydrogen is entrapped in which form? In atomic form, because at high temperature hydrogen is converted to hydrogen atom. What I am telling, understand? This hydrogen atom generally it is entrapped at high temperature level in the grain spacing zone of, you can say grain spacing zone of the heat affected zone. This you should keep in. Let us consider this is your heat affected zone. Here generally let us consider I am drawing the grain which is little bit bigger way I am drawing, okay, for your understanding purpose only. Okay. Let us, these are the grain. Okay. Now, you see these grain generally, this is generally you can say grain, and this small void is there, you see, you can see these are the void is there or grain spacing is there. So, this there is a small void is there. So, what happens when the fusion zone or weld zone is start cooling, at that time generally what happens, the hydrogen atom, this is the hydrogen atom, this hydrogen atom generally try to move in atmospheric direction as well as heat affected zone direction. Heat affected zone direction means, heat affected zone is I have already told you just outside of fusion zone, okay, and outside of the fusion zone to recrystallization temperature zone. So, what happens in this small spacing zone, this hydrogen atom start moving, and in this small grain spacing zone it entrapped in this grain spacing zone, hydrogen atom entrapped at high temperature level. So, this once this hydrogen atom entrapped in this what it is called grain spacing zone, then this hydrogen atom generally at atomic level, one thing you should keep it in mind, volume of hydrogen atoms I am representing Hv and volume of hydrogen molecule I am representing H2V. Always you should keep it in mind, this hydrogen atom at high temperature level is stable, but once it is start cooling at a particular temperature is around 600 degree Fahrenheit, that means below 600 degree Fahrenheit, or it is also below you can say 316 degree centigrade temperature, below 316 degree centigrade temperature, these hydrogen atoms become very unstable. What I am telling, understand? And this hydrogen atom chain again start combining together and form hydrogen molecule H2 gas. So, one thing you should keep it in mind, hydrogen molecules volumes is much higher than hydrogen atom volumes. What I am telling, understand? Due to this volume difference, what happens in this grain spacing zone, once this grain spacing zones, once here hydrogen molecule start forming, this hydrogen molecule start forming after cooling, then it volume increase, then on its volume increase it create tremendous pressure, you can see it create huge pressure on this grain spacing zone. Due to this tremendous pressure, what happens, this grain, whatever the grain are there, let this grain spacing zone. So, whatever the grain is there, this grain boundary generally start separating, it start moving, that means crack start to generate as well as it start to propagate. Due to what? Due to formation of hydrogen molecule at room temperature. What I am telling, understand? Hydrogen atom has low volume than hydrogen atom, that is why due to high volume it creates high pressure on this grain spacing zone, and due to this high pressure grain boundary separation start taking place. Due to this crack start propagating, and what happens, finally fracture is taken place. This phenomena is known as hydrogen embrittlement phenomena. Now, for occurring this grain boundary separation, generally this grain should have some quality. What is this quality? This grain should also have hard grain. If it will be ductile grain, what happens? Due to this high pressure it can deform. What I am telling, understand? That is why what happens, this grain also should have hard grain. What is this hard grain? That is why I have told you, a susceptible microstructure, that means high microstructure or high grain is required. That is generally to get this phenomena, generally here it is required martensitic types of a structure. What I am telling, understand? Apart from these things, this crack propagation or this cold cracking phenomena also enhance if there will be some internal stress, that is internal residual stress which is tensile in nature. This you should keep it in mind. Tensile types of residual stress, if it will be there, then it helps to propagate that cracking. That is why I have written a threshold tensile stress, some minimum tensile stress also is required to separate this, what it is called, grain boundary. Okay. This is called generally hydrogen embrittlement phenomena or cold cracking phenomena. Why it is hydrogen embrittle phenomena? You got the idea. Due to this hydrogen atom convert to hydrogen molecule which create high pressure. Due to this high pressure, as this cracking is taken place, that is why it is called hydrogen embrittlement phenomena or cold cracking, as it is taken place at cooling condition, that means at room temperature level, that is why it is called generally cold cracking phenomena. Here one thing you should keep it in mind, in last lecture itself I have told you in TTT diagram, if cooling rate is critical cooling rate, then you will get martensites at the end, but what happens if the cooling rate further increase, then also you will get martensite. So, I have already told you, if cooling rate become faster and faster, your martensite type will be harder and harder. This you should keep it in mind. That is why some very important points here I have written. In general, always you should keep it in mind, a higher level of hydrogen will require a lower threshold stress for onset of cold cracking. That means, if the hydrogen level is higher, then what happens, your threshold value of stress can be lower, because that high level of hydrogen will create high level of pressure. To get this phenomena, the temperature is generally below 600 degree Fahrenheit, or in terms of centigrade it is 316 degree centigrade. This you should keep it in mind. Now, I have already told you T8/5 or tau 8 by 5, which is a very important phenomena in case of welding final microstructure, to avoid what it is called this hydrogen embrittlement phenomena, as well as to avoid this coal cracking phenomena. Generally this T 8 by 5 is very important. How to calculate this T 8 by 5, that generally I am going to show here. This is a very important topics, you can say. For calculating or estimating this T 8 by 5, there is a standard procedure are there. This procedure was developed by IIW, you can say. IIW, in the sense, the full form of IIW is what is called International Institute of Welding, this you can say. So, for estimation this T 8 by 5 or tau 8 by 5, generally there we use a specially developed carbon equivalent, which is representing as Ce star. This specially developed carbon equivalent generally especially used for estimation of this T 8 by 5, always you should keep it in mind. A relationship generally has been formulated to establish the critical time. This, by using this C star, a relationship has been formulated to establish the critical time T 8 by 5. This T 8 by 5 is should be such so that our heat affected zone should be martensite free in case of low carbon alloy steel. Okay. So, to get martensite free structure, generally this T 8 by 5 what it should be, that you can generally calculate by using this especially developed carbon equivalent. What I am telling, understand? What is this especially developed carbon equivalent Ce star? This is here I have shown. You see it is percentage of carbon plus manganese percentage by 3.6, nickel percentage by 9, copper percentage by 20, chromium percentage by 5 and molybdenum percentage by 4. And one thing you should keep it in mind, this Ce star generally depends on percentage of carbon of this low carbon alloy steel. If this percentage of carbon is less than equal to 0.3, then directly we can put this percentage of carbon star, this should be equal to directly only percentage of carbon you can use. But if this carbon percentage is greater than 0.3, then there we need to use, instead of this carbon percentage, there we need to use percentage of carbon by 6 plus 0.25. This you should keep it in mind. This is a very important calculation you need to know. Okay. So, after calculating this Ce star by using this following formula, you see log tau 8 by 5 2.69 Ce star plus 0.321. This is experimentally established phenomena, what I am telling, understand. So, by this you can easily find out what is tau 8 by 5. That is why here I have written, once you calculate this T 8 by 5, so your time is now known. That means, what should be the time required from 800 to 500 degree centigrade temperature. That means, you from this you can get the cooling rate. So, this cooling rate once you know, then based on this cooling rate you can estimate what? You can estimate this, because this cooling rate is depends on preheating temperature. I have already shown you in previous calculation of cooling rate, there I have shown it is depends on preheated temperature, it is depends on welding parameters, that means Q, that means eta VI, welding speed. So, it depends on that, it is also depends on for thin plate thickness of the plate G. So, these are the different parameters. So, what happens for a particular thickness of plate, if you calculate this cooling rate based on this tau 8 by 5, then you can decide what should be your preheating temperature, what should be your welding parameters, that you can easily estimate. What I am telling, understand, because based on those relationship which I have discussed detailed in previous lecture. So, here another things you should keep it in mind, generally a higher TPAs, you know, if your TPAs is higher, generally we know your cooling rate is decrease, correct. So, that is why what happen, cooling rate is decreased, that means it takes high time to cool from 800 degree centigrade to 500 degree centigrade. That is why, because we know dT by dt, I have already shown you for thin plate, T minus T preheating temperature to the power q, you can say. Now, I have already shown there that this cooling rate is proportional to, or you can say if this TPA is increase, then you can say dT by dt is decrease. dT by decrease means it takes more time to cool, correct. That is why I have written higher the TPA is result in larger tau 8 by 5 or T 8 by 5, definitely it will take more time. So, your time required from 800 to 500 degree centigrade temperature also will be more, this you should keep it in mind. Now, I will discuss about how to estimate preheating temperature. Now, there are 10 different you can say methods are there to estimate preheating temperature. This 10 different method is based on, you can say 10 different chemical carbon equivalent formulation. So, what happens for a particular chemical equivalent formulation used for a particular types of steel material, for different types of material, different types of carbon equivalent formula generally established. So, that is why here I have written that a particular carbon equivalent formula derived for a specific set of steel may not be accurate for steel which is outside the family of this steel. So, for a particular group of steel there is a particular chemical equivalent, for other group of material this chemical carbon equivalent or carbon equivalent is different. So, in this lectures I will mainly focus those steel plates which have a wide application in the field of manufacturing industry, which are widely used. So, that is why here mainly we will focus those steel material and those carbon equivalent which are generally required for which have wide application, that you can say. So, one thing here you should keep it in mind, carbon equivalent of a steel can be taken as a rough guide for what it is called evaluation of the weldability. Now, first of all you should know what is weldability. Weldability means the capacity of a material to be welded under fabrication condition imposed into a specific design structure, and also whatever the welded structure it will be developed, that welded structure performs satisfactorily in service, that is called the weldability of that material. What I am telling, understand? That means it should be welded as well as it should perform satisfactorily, that is generally termed as weldability. What I am telling, understand? So, this chemical equivalent, chemical carbon equivalent generally we taken as a rough guide for this weldability estimation. Many other condition also such as preheating requirement, use of hydrogen electrode and post weld heat treatment can be related to this carbon equivalent. What I am telling, understand? One thing here you should keep it in mind, generally in case of preheating requirement, post weld heat treatment requirement and its weldability type, generally this carbon equivalent generally we take as a rough guide. How it is? Generally this carbon equivalent is based on what it is called percentage of composition of the parent material. Generally this carbon equivalent is, if it is less than 0.35, in some book it is written as 0.4 also. Okay. So, if it is 0.35, then generally your weldability of the what is called material is good. If this carbon equivalent, so you can say good weldability. That means, here no preheating, no post weld heat treatment is required, that you can say. Now, once this carbon equivalent greater than 0.35, then you see your weldability is poor. So, here generally you can say your weldability become poor, what I am telling, understand. Now, if the chemical equivalent which is varying from 0.35 to 55, chemical carbon equivalent it is called, or simply carbon equivalent also you can say CE, carbon equivalent. If this carbon equivalent within this range, then your weldability is poor. For that, within this range, once your carbon equivalent is there, then what are the things required? Here you need to use preheating, as well as here generally low hydrogen electrode is recommended. Generally here you should use low hydrogen electrode, you should use during welding, that welding electrode should have low hydrogen content. Now, if the carbon equivalent is greater than 0.55, in this case generally here preheating plus after welding also post weld heat treatment also required, post heating also required, post weld HTIM, it is in short term post weld heat treatment also are required. These are the things you should keep it in mind. So, this chemical carbon equivalent is generally considered as a guide where we should require preheat types of heat treatment, where we should require post weld types of heat treatment required. Generally this carbon equivalent formulation for plain carbon steel, here you can write for plain carbon steel this chemical carbon equivalent is equal to, you can say percentage of carbon plus, it is plain carbon steel generally manganese silicon is a alloying element. So, that is percentage of manganese plus silicon divided by 4. Okay. This is generally for plain carbon steel, where generally carbon plus manganese silicon composition are there. These are all weight percentage, this you should keep it in mind. Now, for low alloy steel, this carbon equivalent you should know is equal to your percentage of carbon plus manganese by 6. Low alloy steel means it is a composition of different alloying elements like manganese, molybdenum, chromium, vanadium, these types of alloying elements are there, plus percentage of molybdenum divided by 4 plus percentage of nickel divided by 15 plus chromium divided by 5 plus vanadium divided by 5. Okay. This you should keep it in mind. This low alloy steel generally if it has what is called silicon and copper element also if it is there, then by what is called International Institute of Welding IIW, they propose generally carbon equivalent for those material is percentage of carbon plus manganese by 6 plus chromium plus molybdenum plus vanadium by 5, all are percentage, always you should keep it, plus percentage of silicon, nickel plus copper divided by 15. So, these are the very important chemical carbon equivalent for low alloy steel, because generally for low alloy steel you know your preheating or post weld heat treatment generally are required, which is calculated based on this carbon equivalent. Means when you require preheating operation, when you require post weld heat treatment requirement, that you can estimate from this chemical carbon equivalent. Okay. Now, first of all I will discuss about how to estimate this preheating temperature using a very important method. Actually I will discuss, instead of discussing different method, I will generally concentrate on 2 different method only. The first method I will discuss which is based on European standard, that is EN 10112 method. Generally this method also referred to as hardness control method. This method is generally based on assumption that coarse grain heat affected zone hardness is kept below a certain value. If we can keep this coarse grain heat affected zone hardness below some certain critical value, then the risk of coal cracking can be avoided or coal cracking can be reduced drastically. Here generally the hardenability of steel is represented by chemical carbon equivalent, which is given by International Institute of Welding, which is adopted by International Institute of Welding in 1967, which is nowadays also very popular for estimation of preheat temperature. Now, you see coarse grain heat affected zone. What is coarse grain heat affected zone? That things in details here I have discussed. Like you see in case of welding, the fusion zone, this is the fusion zone, just near the fusion zone there is a zone where the grain size is little bit coarse in nature, that means larger grain size is there. This is generally varying from fusion boundary to around 1100 degree centigrade temperature. After that there are generally fine grain heat affected zone is there. That fine grain heat affected zone is generally within a range of 1100 degree centigrade to around 850 degree centigrade temperature, and after that generally another heat affected zone is there, that is zone is called generally intercritical heat affected zone. Like these types of different zone are there. So, this I have just showing for your understanding purpose. What is this CGHAW? CGHAW means coarse grain heat affected zone, which is close to fusion zone, because there is a chance of hydrogen embrittlement phenomena is more. This you should keep it in mind. So, according to carbon equivalent by using International Institute of Welding, I have already discussed in previous slide. Here also I have written this carbon equivalent formula, that is carbon percentage plus manganese by 6, chromium, molybdenum and vanadium by 5 and copper plus nickel by 15. This I have already discussed in previous slide. So, first of all you need to calculate this carbon equivalent. Once we calculate this carbon equivalent, then by using Escoda method you can estimate what is TPH. TPH means preheat temperature. So, that means for this welding process, for this welded material, what should be the temperature requirement, so that your weld quality should be martensitic or martensite free, that you can say. That means your weld chances of what it is called cracking is less, coal cracking is less. So, by using this formula like TPH can be calculated like 450 degree centigrade square root of carbon equivalent according to IIW minus 0.42. Based on this formula, once we calculate the what it is called preheat temperature, based on this preheat temperature, if we will do the welding, then what happens, chances of cracking will be less. Now, here one things you can observe, here we have not considered any thickness effect of the plate. So, for any types of plate thickness, these types of preheating can be used. This is a process generally where thickness is not considered as a parameter. In next case, where actually I will discuss about estimation of preheating temperature considering what, plate thickness. So, how to calculate this preheat temperature? This method was proposed by Seperian. You see this Seperian who generally proposed this method. Here also this method we can use for low alloy steel plate. Okay. So, here generally this method considered thickness effect in the plate. So, what is the formula he proposed? He proposed that preheat temperature should be equal to 350 degree centigrade temperature into C minus 0.25. What is this C? This C is generally equal to carbon equivalent into 1 plus 0.005 thickness of the plate G. So, always you should keep it in mind, these all are in percent, okay, but this unit is in centigrade. Okay. So, this G is thickness of the plate in millimeter, and carbon equivalent whatever the things you will get, this should be put as a percentage of carbon equivalent, and 350 degree is it in centigrade. Okay. So, by this generally you can easily calculate what is the preheat temperature of the material. So, you see this C in bracket, this is also generally called total equivalent carbon. Okay. This is also sometimes called. Now, one problems I will solve, then it will be very clear to you. For a butt welding operation of 10 millimeter thick low alloy steel plate, this should be the calculate the preheat temperature. For a butt welding operation of 10 millimeter thick low alloy steel plate, calculate the TPH. So, here this plate material composition are carbon percentage is given as 0.23%, manganese is given as 0.8% and molybdenum is given as 0.133%. Okay. Based on these things, we need to calculate what is the, just here little bit modification I am just doing. Okay. 0.25. So, the problem statement now I am going to discuss. So, now we will solve one problem on preheating temperature calculation considering thickness of the plate. Like for a butt welding operation of 10 millimeter thick low alloy steel plates, calculate the TPH, that means preheating temperature, if the composition of the plate material are carbon percentage is 0.28%, manganese percentage is 0.8% and molybdenum percentage is 0.25%. So, for calculating the preheat temperature, what are the steps we need to follow? First of all, we need to find out what is carbon equivalent. So, carbon equivalent formula I have already shown you. For low alloy steel, it is percentage of carbon, manganese by 6 plus molybdenum by 4 plus nickel by 15 plus chromium by 5 plus vanadium by 5. Now, here this percentage of carbon given as 0.28 plus you see molybdenum is 0.25, manganese is 0.8 by 4 and molybdenum is given as 0.25, other alloying element is not available. So, we are not considering this thing. molybdenum divided by manganese by 6, molybdenum by 4. So, this will give you a value which is 0.476 percentage. Now, we need to calculate the total C as considering the thickness of the plate, that is your Ce, total carbon equivalent carbon equal to Ce into 1 plus 0.005 G. This is actually coming as plus 0.005 into G means 10. So, this will give you a value which is equal to 5%. Now, what is the preheating temperature? So, the TPH you can calculate as 350 degree centigrade into C minus 0.25 square root, that means to the power half. Okay. Okay, this will give you a value which is 175 degree centigrade temperature. So, by this generally you can easily find out what is the preheating temperature. So, by considering this preheating temperature, if you do the welding for this plate, what happens? The chances of hydrogen embrittlement phenomena or chances of coal cracking phenomena will be eliminated. Okay. Now, based on this preheating temperature, then you can calculate what is your what is called cooling rate, that also you can calculate. That is why what happens, like the welding parameter used for this above welding plate 10 millimeter thick plate, if it is 300 ampere current, 25 volts, welding traverse speed is 8 millimeter per second, and the thermophysical property, or if it is given K is also given, then you need to find out what is the cooling rate. So, what is the steps you need to follow here? Now, the step you need to follow for finding out the cooling rate, first of all you need to find out your G bar, that means dimensionless thickness. This is first of all you need to find out dimensionless thickness. Okay. What is your dimensionless thickness? If this dimensionless thickness is less than 0.9, then you should use two dimensional types of cooling rate equation. If this dimensionless thickness greater than 1.2, then you need to use what it is called three dimensional types of if this G bar is greater than 1.2, then three dimensional cooling rate equation you need to use. What is three dimensional types of cooling rate equation? You know this thing, dT by dt is equal to generally 2 pi k V by q T minus T0 square, and two dimensional equation also know, and dimensional equation calculation generally you need to use plate thickness G into rho C V by q T minus T0. Here T0 means T preheating temperature, always you should keep it in mind. Okay. By using these things you can easily find out what is the dT by dt, that means cooling rate, this you can easily find out. So, this all about your preheating types of preheating calculation. Okay. Now, we will discuss about the interpass temperature, that means in case of a multipass welding process, what should be our interpass temperature. One thing here you should keep it in mind, generally for interpass temperature, our temperature range can be a minimum temperature, a maximum temperature, or it can be a maximum or minimum both the temperature. What I am telling, understand? Generally a general rule is there for technical community, generally it is suggested, that means minimum interpass temperature should be equal to preheating. What is interpass temperature? Means for multipass welding, for one pass, for subsequent two pass, in between what should be the second pass starting temperature. What I am telling, understand, which generally act as a preheating temperature of for second pass, that you can say. So, it is suggested that for minimum generally this interface temperature should be equal to, here I have already written the minimum specifying preheating temperature. That means, I have already told you what is the preheating temperature generally specified in previous slides. Like I have already told you, it should be generally approximately equal to what is called martensitic starting temperature. So, interface temperature also should be within that range, that means it should be approximately equal to martensitic, that means it should be about martensitic starting temperature. Okay. If the interface temperature is within that range, then what happens, your chances of boil quality, that means chances of cold cracking types of phenomena will reduce drastically. This you should keep it in mind. That is why to reduce or it will eliminate the risk of cold cracking. Now, this interface temperature generally for low alloy steel it can be like this, okay. But for some material where generally the microstructural changes is not generally affected much during cooling. Like here I have already written here, for those types of material that is required to use some maximum interface temperature level. Like some material are there like 300 series stainless steel we may consider here. In case of 300 series stainless steel, it is also called non hardened by heat treatment steel. What does it mean? Means this steel material generally does not convert what it is called austenite to martensite when it is cooled down from welding temperature to room temperature. That means, here no martensitic temperature is taken place. Here what we can do, we can avoid preheating types of phenomena to controlling this minimum what it is called preheating temperature, since here there is no risk of cold cracking. So, here we can eliminate this preheating, but here one thing you should keep it in mind. It is important to define a temperature corresponds with the onset of loss in corrosion resistance. This temperature would be specified as TIP max, what I am telling, understand. But it is observed that what happens in between two consecutive pass, if your temperature goes above some particular temperature range, then what happens, there is a chance of what happens, less corrosion resistance, or you can say there is a chance of loss of corrosion resistance. So, that is why weld temperature between pass should then be controlled so as not to exceed TIP max in order to retain corrosion resistance of the steel. This you should keep it in mind. Apart from this thing, controlling this TIP max, it is also important in case of quenched and tempered steel. Generally exceeding this TIP max in case of this quenched and tempered steel can have adverse effect on strength, toughness and fracture toughness. This you should keep it in mind, because interface temperature should have a maximum limit. If your interface temperature above this maximum temperature, then there is a chance of what is called corrosion resistance decrease drastically. So, it should maintain a maximum interface temperature level. Beyond that maximum level we should not go. If we go beyond that maximum interface temperature level, then there is a less corrosion resistance, as well as some other material. If we cross that maximum temperature interface temperature limit, that means then there also is a chance of adverse effect, that is it can adversely affect on a strength, toughness and what is called fracture toughness. So, this all about today's lecture. So, these are the references which I have followed for this lecture. So, in next lecture I will discuss about another important heat treatment process, that is post weld heat treatment process, its different categories, in details. Okay.